Digestion, then we'll finish digestion on Monday, and test on Wednesday, right? Yeah, 3 chapters. Respiratory, urinary.
Are we doing an IRL?
I don't think we'll have time. I mean, unless I butt through this today, but I don't really want to do that, so I don't think we'll get it in. So, quick little review of the functional unit of the kidney. The nephron itself, remember that the blood comes into the kidney. One of the main jobs of the kidneys is to filter the blood, and the renal artery branches and branches and branches into the afferent arteriole. Afferent arteriole branches into the glomerulus, which is a capillary bed. Capillaries are single cell thick, stuff goes across capillaries. Capillaries are leaky. Leaving the capillary bed is the efferent arteriole, and the efferent arteriole is then going to branch into another capillary bed, which is known as the peritubular capillaries. So what comes out of the glomerulus is, we said, fluid, plasma, and when plasma leaks out of the blood vessels, now we got to call it something else, because it's not in the blood vessel anymore, so it can't be called plasma, so we're going to call it filtrate. Filtrate is the fluid that has been pushed out of the capillary, out of the bloodstream. So that plasma, which has ions and nutrients and wastes and stuff, and the dissolved stuff, that's what leaks out. And once it leaks out, we're going to call it filtrate because it's caught by the Bowman's capsule. It's going to go into the proximal convoluted tubule, loop of Henle, distal convoluted tubule, collecting duct. Collecting duct's going to dump into the center of the kidney, the ureter, and the bladder, etc. And remember, we said that good stuff and bad stuff get filtered out of the glomerulus. Things like uric acid and urea and breakdown products of protein digestion, which are toxic and they have to be excreted. But we also get rid of good things like glucose. That's one of our things that we do filter out. And then that glucose is going to be reabsorbed back into the bloodstream here at the level of the peritubular capillaries. And most of that occurs at the beginning, at the proximal convoluted tubule. So that's the physiology part that we're going to talk about. How does that stuff get back in? So, filtration. Filtration is what happens at the level of glomerulus. So plasma, liquid part of the blood, in the bloodstream, in the capillary, is called plasma. Once it leaks out, it's called filtrate. Remember that our capillaries are leaky, and if you remember the image that we talked about with regular capillaries, like so, right? And we said on the arterial end, we've got a pressure of 37. On the venous end, we've got 17. And on the outside, we've got 25, right? So more fluid leaks out than comes in. 12 leaks out, 8 comes back in. In the glomerulus, the hydrostatic pressure here is 55. So it's much higher. So that means we're going to leak out more fluid because it's higher pressure than any osmotic pressure that's pushing against it. What doesn't come out of the glomerulus under homeostatic conditions, under normal conditions, are big things. We're not supposed to have blood in our urine. We're not supposed to have blood cells, red blood cells, white blood cells, platelets. Those aren't supposed to be in the urine. We aren't supposed to have protein in our urine. Maybe trace amounts if you had a big meal, but we're not supposed to have big proteins either. If you do have those, that means you've got kidney issues. You've got inflammation of the kidney, maybe a UTI, something that is causing damage or inflammation or pressure within the glomerulus or the nephron. So what comes out of the glomerulus, that filtrate, is known or produces something called the GFR, the glomerular filtration rate. And that's a measurement. We can measure that. If you have a blood test, there's always a measurement on there called eGFR. GFR, it's your glomerular filtration rate. Normal glomerular filtration rates for normal people with normal kidneys is greater than 90. Greater than 90, which is, I think, I can't remember the measurements of it. Usually they show less than, they have a number on your blood test as like less than 60, but normal functioning GFR should be 80 to 90 or greater. When your GFR goes down, that means you're not filtering like you're supposed to. You're not, and if you're not filtering, what are you not getting rid of? Wastes, right. And when those wastes build up, you can see that on a blood test too, in things like something called BUN, blood urea nitrogen. That means that's a waste product that's supposed to be in the urine. It's not supposed to be in the bloodstream. So if your BUN goes up, your kidneys are bad. Creatinine, or creatine, is another one. When that goes up, that's a waste product. It's supposed to go out in the urine. That goes up, that tells you your kidneys are bad. As I said, normal GFRs are 80 to 90 or greater. My nephew had a liver transplant, and while his liver was tanking, it created a bunch of, it was high blood pressure in the organs. Remember we talked about ascites and no, we didn't talk about that because we haven't done digestion yet. When your liver tanks, it can't take the blood from your intestines and your organs and your kidneys, and that puts very high pressure in those organs, and it can actually result in kidney failure if you have a bad liver. So his kidneys were not good, his liver was terrible. He got a liver transplant, but his kidneys are not normal. His GFR runs 50, in the 50 range. And the older we get, the kind of worse our kidneys kind of run. It's just sort of the way aging goes. And the worse your kidneys are, the more toxins you don't get rid of, the more toxic byproducts you don't get rid of, and the worse it is for you. So the level of dialysis, you won't get dialysis until your GFR is at 15 or below. So you're sitting there at 20, you got some crappy kidneys, and you're gonna have some byproducts that are sitting around in your bloodstream, but dialysis doesn't occur until 15 or less, which seems really bad. And then once you get to dialysis, then you're gonna be looking at a kidney transplant. So, here's our glomerulus, here's our afferent arterial, here's our good stuff and bad stuff. The purple is the small enough structures that can leave the glomerulus. The green are too big, they can't leave. Remember, these purple ball structures represent toxins as well as tiny little molecules that we want to bring back in. So, how do we bring this in? As I said, most of the reabsorption occurs at the level of the proximal convoluted tubule, the first twisty tubule after the Bowman's capsule. So we're going to have our Bowman's capsule like so, and we're going to have our proximal convoluted tubule. I don't know, however that's going to go, whatever, like that. Proximal convoluted tubule is single cell thick. It's made up of simple cuboidal epithelial cells, cube-shaped cells. Single cell thick. Gosh, it'd be important that it's single cell thick, and the capillary is single cell thick too. Then we've got our glomerulus. Afferent arterial coming in, glomerulus, efferent arterial leaving. And remember, the efferent arterial is going to come back around and form the peritubular capillaries. Capillaries are single cell thick too, right? They just happen to be simple squamous cells. And here's what we need to do. We've got good stuff and bad stuff that got filtered out in the filtrate, right? It's going to run through our little nephron. The bad stuff's going to stay in the tube and head out in urine, but we want to bring this good stuff back into the bloodstream. And this is what happens. The example that we're going to look at is glucose. Other molecules get reabsorbed in a similar manner, but we're just going to look at glucose here. So, if this is my little glucose molecule, we want to bring all the glucose back in the bloodstream. We don't want sugar in our urine. We want to keep it in our bloodstream so we can send it to the cells and make ATP. So what we're going to do is we're going to reabsorb glucose through the cuboidal cell, through the interstitial fluid, and back into the capillary. So this is this cell, okay? Here's the interstitial fluid, and here's the capillary, right? So we've taken this and we've kind of stood it up. Does that make sense? All right, this comes from a different book. This is a different book, but it's a really good picture because it makes it really easy to follow. So, inside our proximal convoluted tubule, inside the lumen, what's been filtered out? Good stuff and bad stuff. We've also got sodium that's been filtered out because sodium is a very, very, very tiny little ion. It gets pushed out of the glomerulus. Sodium and glucose are going to bind to a co-transporter on the luminal edge, the lumen side of the cell. Sodium's going to bind, glucose is going to bind. Co-transporter means they both have to bind in order to go across. It's a co-transporter. This protein transports both molecules across, or both structures. They're both going to enter the cell. Once they enter the cell, they're going to go their separate ways. So they come in together, but then they leave separately. Glucose is going to leave the other side of the cell via facilitated diffusion. It's another protein that's going to carry glucose across. Remember, facilitated diffusion doesn't require ATP. It's just diffusion with a carrier, right? So we're going to have high glucose in the lumen, high sodium in the lumen. They're going to bind to the co-transporter. They're going to enter the cell. Now we're going to have a bunch of glucose inside the cell. High concentration to low concentration. Diffusion wants to occur, but we need a carrier. So the protein that's going to carry glucose across is the process called facilitated diffusion. Now we're going to have a bunch of glucose in the interstitial space and lesser in the bloodstream. And what are we going to do again? Diffuse across. Into the capillary, we don't need a carrier. So this is simple diffusion. Simple diffusion through the little holes in our capillary bed around the nephron. We've got these little tiny holes to pull this kind of stuff in. So we go from high concentration to low. Now we're going to build up a bunch of glucose in the cell. High concentration to low. Now we're going to have a whole bunch in here, and we're going to go high concentration to low. It's a lot of diffusion going on. Co-transporter carries the sodium and the glucose into the cell. Facilitated diffusion carries the glucose out, and simple diffusion back into the bloodstream. On the sodium side, we're going to transport sodium across via the famous sodium-potassium pump. Sodium's going to go back into the bloodstream. Potassium's going to be sent back into the cell. And that's how we get stuff back in. Again, other molecules do this too. It's just different processes. And the example we're going to look at is glucose. So remember, this process of reabsorption is occurring mostly at this level. We filter it out and we pull it right back in. The nasty stuff stays in the tubule. There is no mechanism for the bad stuff. There's no receptors for urea, uric acid to come back in. So they don't get an option to be reabsorbed. They end up going up. 60 to 75% of the good stuff is reabsorbed at the level of the proximal convoluted tubule. 67%. Small proteins enter in a little bit different way. They enter by endocytosis and then they're degraded. And then the term saturation. What happens? What does that mean? Saturation. Let's say that you have diabetes. What does it mean? What happens when you have diabetes? Okay, and so what do you get? High blood sugar. So you got a ton of glucose here, right? And all that glucose be filtered into here. So we've got lots and lots of glucose. Excessive amounts of glucose, right? We want to bring that glucose back in. But we can't because there's so much, the nephron can't pull it in. There's just so much of it. Let's use some goofy numbers. Let's say that I have 100 of these glucose receptors to pull 100 glucose molecules back into the bloodstream. 100. That's a lot. 100. If I have 100 glucose molecules, how much am I going to reabsorb? 100% of it. All of it, right? What if I have 1,000? Then I'm going to pull back in. I'm going to reabsorb how much? 100. And what happens to the 900? It goes into the urine. Sugar in your urine. Saturation. All of the glucose receptor sites are saturated. They're already hooked up. You can't bind more than are already bound, right? So we can only bring in so much. All that extra gets urinated up. Then the other thing that happens is when you have all this glucose in your tubule, water wants to osmose in because of all these solids, right? Osmosis occurs. And then what do you have?
High pressure.
You got a bunch of pee, right? What's one other symptom of diabetes?
Lots of pee.
Excessive urination, sugar in the urine. And then when you have excessive urination, because you're getting rid of a lot of water, then you're dehydrated, you're thirsty, right? You have polydipsia, polyuria. You get dehydrated, you try to drink more, but it doesn't always keep up. Throughout the tubule, we also secrete bad things back into the tubule. And we're not going to go into the details of this, but secretion means we're going to go from the blood back to the tubule. So not only can we get the bad stuff out through the glomerulus, we can also send it from the blood into the tubule in an opposite mechanism. So reabsorption goes this way. Secretion goes this way. So if there's anything that's in the bloodstream that we'd like to get rid of a little extra of, we can secrete it from the blood into the tubule and get rid of it that way. If it didn't get filtered out. But we're not going into those mechanisms. All right, the loop of Henle. What is the purpose of this goofy loop of Henle? And there's more details to this than we're going to talk about as well. The loop of Henle is that big hairpin loop from the proximal convoluted tubule to the distal convoluted tubule. And these loops of Henle sit deeper in the center of the kidney, which is a different sort of environment. And the main job of the loop of Henle is to reabsorb water. So water is going to go from the loop back into the bloodstream. What that's going to do is concentrate your urine. Remember, we filter our total blood volume 30 to 36 times a day. We filter 180 liters of fluid per day, but we only make 1 to 2 liters of urine. So the vast majority of that water that's being filtered heads right back to the bloodstream. If you filtered out 180 liters and you peed out 180 liters, man, you'd be in trouble, right? You wouldn't have any plasma left. So, job of the loop of Henle is to concentrate the urine into a smaller volume with higher solids. That process or that mechanism is called the countercurrent multiplier system. All I want you to know is that it concentrates the urine. It reabsorbs water and concentrates the urine. It has to do with the environment. It's a hypertonic environment. Main bullet point from that, concentrates the urine. Reabsorbs water back into the blood. So this is just another picture of what I just showed you. Here we are filtering. We reabsorb good stuff. We make secrete bad stuff from the peritubular capillaries if we didn't filter it out. Oh, would you remember ADH?
Yes.
What is it? Anti-diuretic hormone. What does it do? Where does it come from? Yes, what part of the pituitary?
Anterior.
Posterior pituitary. Comes from the posterior pituitary. Target was the kidney, and what's it going to do? Decrease urine production. So, ADH is secreted when you're dehydrated, right? And that fluid, we want to not make as much urine. We want to keep some of that fluid in the bloodstream. So here's the mechanism of how ADH actually works. It doesn't work at the level of the loop of Henle. It works a little bit later. This is another picture from a different book. Remember, another word for ADH is vasopressin. Whatever. I don't like vasopressin. I like ADH because it tells me what it is. So now we're at the level of the collecting duct. So let's remember where that is in our nephron. Here's the collecting duct. Nephrons empty into the collecting duct. By the time we get to the collecting duct, this is urine. It's water with solids in it. And so here we are sending that urine into the collecting duct. Collecting duct is going to empty into the center of the kidney, which is then going to enter into the ureter. What we're going to do is if we are dehydrated, we're going to release ADH, and it's going to pull some of that water from the collecting duct back into the bloodstream. And here's how it works. Here we are at the collecting duct. Again, the collecting duct is single cell thick. There's the lumen. We've got a bunch of water here. And we want to pull it back into the bloodstream that runs right along the level of the collecting duct. This guy right here, another capillary. So vasopressin, or ADH, is released into the bloodstream because all hormones enter the bloodstream, right? Then they travel to their target organ. So ADH is in our bloodstream. It's going to bind to the cells of the collecting duct because that's where the receptor is. The receptor is on the collecting duct cell. So it binds to the receptor, and what that does is it causes an action inside this cell, and the cell is going to make these water pores. These little water channels, and insert them in the cell membrane, and it's going to pull water from the lumen through the cell, out the other side of the cell, to flow back into the bloodstream. So vasopressin, or ADH, creates these water channels at the level of the collecting duct. Water's going to flow into the cell, through the cell, back into the bloodstream, which makes what happens to the urine then. It's even more concentrated, less volume, and what did we pull in? Water. Did we pull in urine? No. Did we pull in waste products and urea and uric acid? No. Water only. It only pulls the water. So that works at the level of the collecting duct. Kind of fancy little deal there. Don't worry about this. Cross that out. And cross out that whole slide, that whole section. So the next thing we're going to talk about is another hormone that has to do with, it's a mineralocorticoid. Remember where those come from? Adrenal, what part of it? Adrenal cortex, right. Remember your adrenal cortex made glucocorticoids, mineralocorticoids, and a sex hormone. We're going to look at one of the mineralocorticoids. Who tells the adrenal cortex to release these? One of the hormones from the anterior pituitary. Anybody remember what it was?
No.
ACTH. I know, the endocrine system sucks. It's just a hard one. It's like you have it for a while, and then it goes away. I know. So, anterior pituitary releases ACTH. ACTH goes to the cortex, tells the cortex release these hormones. This is one of the hormones. It's called aldosterone. Aldosterone is a mineralocorticoid, and it is going to allow for the reabsorption of sodium. And the whole kind of key here is where sodium is, water follows. Sodium's a solute that water likes to follow. Got a bunch of salt somewhere. Water is going to try to osmose. Osmosis is going to occur. Water follows sodium. What do we need to say about this slide? I don't know. Electrolytes. Things like sodium, potassium, these are your ions. That should be HCO3 ones, not HCO ones. Water consumption must equal water excretion. Sure. If you want to keep your blood volume accurate, you pee out as much as you drink in, right? If you're dehydrated, you don't pee out as much. That's the whole basis of that slide. So now we're going to look at aldosterone. What does aldosterone do? It reabsorbs sodium, and if sodium's going to get reabsorbed, guess what else is going to get reabsorbed? Water. Water. So aldosterone is secreted when sodium levels are low. Aldosterone is secreted when sodium levels are low. And here's another image, comes from another book. When sodium levels are low in the bloodstream, aldosterone is going to be released from the adrenal cortex. It's going to bind to the distal convoluted tubule, bind to receptors on the distal convoluted tubule. Aldosterone is actually it's a fat hormone, so it's going to actually enter the cell, go to the nucleus. And what's going to happen is we're going to make these channels, these sodium channels. And sodium is going to be reabsorbed from the urine and sent back into the bloodstream. Sodium's gonna come into the cell, leave because of the sodium-potassium pump, and enter the blood. And where sodium goes, we're also gonna bring in some water. Aldosterone binds to the cells of the collecting duct, creates these sodium channels. Sodium comes in, leaves by the sodium-potassium pump, and gets reabsorbed back into the bloodstream. This would be a situation in which you have low sodium levels in your blood. You're hyponatremic. That's the fancy word, hyponatremic. In exchange for sodium, you're gonna lose a little potassium, but that's okay. We're gonna pull sodium in, we're gonna lose a little potassium. And the reason we bring that up is for this pathway called the RAS pathway, the renin-angiotensin-aldosterone system pathway. Renin-angiotensin-aldosterone pathway. The very first page of this chapter, I said one of the jobs of the kidneys is to maintain blood volume, and secondarily due to blood pressure. We're gonna alter blood pressure. I told you that the kidney releases two hormones. One was called erythropoietin for blood cell production, and another one we said was renin. Here's the renin pathway. Renin is secreted by cells of the afferent arteriole. So renin is secreted here. It's produced from cells of the afferent arteriole. Okay? Renin's going to enter the bloodstream. Now, they're secreted from the cells of the afferent arteriole, so they don't have far to go, right? They're going to enter the blood right there because they come from a blood vessel. Renin is secreted when you have low blood pressure. If your blood pressure is too low. Too low. What could be the reason? Well, it could be lots of reasons. Could be lots of reasons. But if your blood pressure is too low, the afferent arteriole detects that and secretes renin. What does renin do? Renin enters the bloodstream, and it's going to convert one of the plasma proteins. Remember, plasma proteins are proteins made by the liver. They hang out in the plasma. Like we said, albumin was a plasma protein. We've got lots of these. One of them is called angiotensin. It's an inactive protein as angiotensinogen. It's an inactive protein, unless renin's around. If renin's around, angiotensinogen gets converted into angiotensin 1. Angiotensin 1 is converted by an enzyme in the blood to angiotensin 2. But can angiotensin 1 get converted to angiotensin 2 without renin? No, because you got to have the conversion of angiotensinogen, the precursor, into the angiotensin 1. Okay, so in our bloodstream we have an enzyme. It's called an angiotensin converting enzyme. That's what it does. It converts 1 into 2. But renin converts 0, that's angiotensinogen, into 1. Angiotensin 2 is the protein or the structure, the molecule that does work. It's the active component. And what does it do? Angiotensin 2 causes the release of aldosterone from the adrenal cortex. Causes aldosterone to be released. What do we say aldosterone does? Reabsorbs sodium, and what follows? What's that going to do to your blood pressure? Raise it. Angiotensin 2 also causes the release of ADH. What does ADH do? Makes those water channels in the collecting duct, pulls water back into the bloodstream. What's that going to do to your blood volume? Increase it. What's it going to do to your blood pressure? Increase it. Angiotensin 2 is going to stimulate thirst. What are you going to do?
Drink water.
Drink water. Where's that going to go?
Into your bloodstream.
Into your bloodstream. What's it going to do to your blood volume?
Increase.
What's it going to do to your blood pressure?
Increase.
Oh, thank you. Angiotensin 2 also works at the level of the blood vessels and causes vasoconstriction. What does that do to your blood pressure? Increases it. Angiotensin 2 also goes to the heart and makes you have increased cardiac output. Makes your heart beat faster and harder. What does that do to your blood pressure? Okay, thank you. So the renin-angiotensin-aldosterone pathway raises blood pressure, and it's all because little tiny cells in the afferent arteriole detected low blood pressure and released a hormone called renin. Now, let's think about high blood pressure. Remember I told you one of the go-to drugs was something called lisinopril? It's like one of the first things they put you on, lisinopril and a diuretic. Diuretic's gonna make you pee, decrease your blood pressure. Lisinopril affects this pathway. Lisinopril, so let's do this. We have angiotensinogen gets converted to angiotensin 1, which gets converted to angiotensin 2, right? Who does this conversion?
The enzyme.
Who?
Renin.
Renin. And who does this?
The enzyme.
That enzyme called angiotensin converting enzyme. And then this guy does all that work. He's the one that tells everybody, well, we gotta release aldosterone, we gotta release ADH, we gotta drink stuff, we gotta vasoconstrict, we gotta make the heart beat faster, okay? Lisinopril is an angiotensin converting enzyme inhibitor. That's a big word. Where does it work?
Between 1 and 2.
It blocks that. It's an ACE inhibitor. It blocks this. So if you can't convert that to that, what can't you do?
Increase your blood pressure.
You can't do all the work. That's the level it works. Remember, what percentage of high blood pressure do we know an exact cause?
Not
5%, 95%. It's a crapshoot. So we start with this. So if you block the converting enzyme, you block this pathway, which helps to reduce, which helps to not raise your blood pressure. It doesn't necessarily reduce it, it helps to not raise it under circumstance. Then you add that diuretic, which makes you pee more, your blood pressure drops, and we block that to keep it, to continue to raise it up. And some people you can't do both. Some people you can't have the diuretic, like my mom. Her blood pressure was high, but it wasn't horrible. Diuretic dropped it too much, so she just stayed on the lisinopril, which kept it, you know, kind of at an even keel. Does this make sense? Dang it, we had to go back to the endocrine system. There's another hormone called atrial natriuretic peptide, and that comes from your atrium. Comes from the upper chamber of the heart, and it's stimulated by stretch in the upper chambers. The exact mechanism is actually, they do know the mechanism now. Before it was unknown. It works. I had it in my head at one point.
Is that just kind of doing the same thing? Like,
It decreases blood pressure. This one is actual blood pressure decreaser. The other one, like lisinopril, just doesn't raise your blood pressure, right? It blocks the elevation of blood pressure. This one actually decreases blood pressure, and I can't remember the mechanism. I think maybe it works the level of blood. I don't know. Somebody look it up. mechanism of A and B. Oh, I knew, it has to do with sodium and water excretion. Has to do with sodium and water, it tells me right there, sodium and water excretion. So we're gonna, and remember, where sodium goes, water follows. So instead of pulling sodium back into the blood, we're gonna go the other direction. I just can't remember at what level it works. Let's see, acid-base regulation. If you're acidic, what do you suppose your kidneys are going to secrete? Hydrogen ions. If you are acidic, remember, secretion is from the blood to the tubule. We're going to get rid of excess hydrogen ions. And if you are alkalosis, what's going to happen? You're going to reabsorb hydrogen ions. You're going to reabsorb. So acidosis and alkalosis can be affected by your breathing rate, right, because of CO2, and at the level of the kidney, but at the level of the kidney, it's all about hydrogen ions. It's all about getting rid of excess hydrogen or keeping it. Sometimes we can also work with bicarbonate. We can reabsorb bicarbonate. Sort of reabsorb the bicarbonate, secrete the hydrogen. Mostly it's a hydrogen thing. Diuretics like Lasix. Lasix is called a loop diuretic. Anybody know where it works? At the loop of Henle. Yes. That's why it's called a loop diuretic. Not because it forms a loop, but it works at the level of the loop of Henle. And what it does, remember, what did I say the loop of Henle does?
Absorbs water.
Concentrates the urine and pulls water from the loop of Henle back into the bloodstream. Well, guess what diuretics do? If normally we're going to pull water back into the bloodstream here, guess what diuretics do?
Opposite. Which is
They block it from happening. They block the reabsorption of that. So we don't reabsorb the water at the level of the Henle. Which means, where's the water going to stay? In the loop of Henle, and then increase urine production, which helps to decrease fluid. GFRs. I knew I had a sheet in here somewhere. GFRs in women. Normal range for GFR in women, 75 to 115 mils per minute. That's how it works, mils per minute. Men, 85 to 125. I told you it's greater than 90, but there's a range. Women, 75 to 115 milliliters per minute.
75 to 115.
Yep. And men, 85 to 125.
And that's mils per minute.
Mils per minute. That much fluid gets filtered through your glomeruli in your kidneys, both kidneys, per minute. And you keep doing this day after day after day, minute after minute, which filters your bloodstream multiple times a day. Filters your blood volume multiple times a day. Remember, each kidney has about 1 million of these little guys. You got about 2 million little nephrons working all the time. And while 100 mils doesn't seem like much, actually I think it seems like quite a bit. 100 mils doesn't seem like much. When it happens every minute, it adds up to a lot of fluid to be filtered, cleansed. Etc. All right. that's the end of that story.